If you lined up all the blood vessels in your body, they'd be 95,000 kilometers long. And every day, they carry the equivalent of over 7,500 liters of blood, though that's actually the same 4 or 5 liters recycled over and over, delivering oxygen and precious nutrients like glucose and amino acids to the body's tissues. All that blood exerts a force on the muscular walls of the blood vessels. That force is called blood pressure, and it rises and falls with the phases of the heartbeat. It's highest during systole, when the heart contracts to force blood through the arteries. This is your systolic blood pressure. When the heart is at rest between beats, blood pressure falls to its lowest value, the diastolic pressure. A typical healthy individual produces a systolic pressure between 90 and 120 millimeters of mercury, and diastolic pressure between 60 and 80. Taken together, a normal reading is a bit less than 120/80. The blood traverses the landscape of the body through the pipes of the circulatory system. In any plumbing system, several things can increase the force on the walls of the pipes: the properties of the fluid, extra fluid, or narrower pipes. So if the blood thickens, a higher pressure is needed to push it, so the heart will pump harder. A high salt diet will lead to a similar result. The salt promotes water retention, and the extra fluid increases the blood volume and blood pressure. And stress, like the fight or flight response, releases hormones like epinephrine and norepinephrine that constrict key vessels, increasing the resistance to flow and raising the pressure upstream. Blood vessels can usually handle these fluctuations easily. Elastic fibers embedded in their walls make them resilient. But if your blood pressure regularly rises above about 140/90, what we call hypertension, and stays there, it can cause serious problems. That's because the extra strain on the arterial wall can produce small tears. When the injured tissue swells up, substances that respond to the inflammation, like white blood cells, collect around the tears. Fat and cholesterol floating in the blood latch on too, eventually building up to form a plaque that stiffens and thickens the inner arterial wall. This condition is called atherosclerosis, and it can have dangerous consequences. If the plaque ruptures, a blood clot forms on top of the tear, clogging the already narrowed pipe. If the clot is big enough, it can completely block the flow of oxygen and nutrients to cells downstream. In vessels that feed the heart, that will cause a heart attack when oxygen-deprived cardiac muscle cells start to die. If the clot cuts off blood flow to the brain, it causes a stroke. Dangerously clogged blood vessels can be widened by a procedure called an angioplasty. There, doctors thread a wire through the vessel to the obstructed site, and then pass a deflated balloon catheter over the wire. When the balloon is inflated, it forces the passageway open again. Sometimes a rigid tube called a stent is placed in the vessel to help hold it open, letting the blood flow freely to replenish the oxygen-starved cells downstream. Staying flexible under pressure is a tough job for arteries. The fluid they pump is composed of substances that can get sticky and clog them. And your typical healthy heart beats about 70 times a minute, and at least 2.5 billion times during an average lifetime. That may sound like an insurmountable amount of pressure, but don't worry, your arteries are well suited for the challenge.
Do you remember tripping over as a kid and cutting your knee, and then magically the bleeding suddenly stops? Or have you ever wondered why this happens? Our body is very clever and produces substances to seal off the open wound. In this video, we are going to look at how and why blood clots. Clotting prevents us from bleeding to death, and also protects us from nasty disease-causing organisms called pathogens entering our body. When we injure ourselves, we can damage the blood vessels just below our skin. This can cause blood to either leak into our tissue and form a bruise, or if the skin is broken, to openly bleed. To prevent these horrible things happening, blood clotting occurs. So let's have a look at how this happens. Starting with platelets. These are tiny cell fragments that float around in our blood. When a blood vessel is damaged, collagen is exposed. This collagen exposure attracts platelets to the injured area.
In a first step towards clot formation, platelets are recruited to the site of vessel injury by now exposed molecules of the vessel wall, such as collagen and von Willebrand factor. This factor mediates the linking of platelets to collagen via a specific receptor in the platelet membrane. The resulting change of shape of the platelet from its resting state into the dendritic form indicates activation. The activated platelet in turn releases prothrombotic molecules such as adenosine diphosphate, ADP. By binding to its receptors, ADP induces aggregation. And recruits further platelets to the site. Thromboxane is another important mediator of platelet activation and aggregation. Under its influence, the platelets cross-link with each other. These interlocking mechanisms cause platelet activation to snowball. The clot grows rapidly. Activated platelets also trigger the coagulation cascade and thus the formation of thrombin. Thrombin, in turn, stimulates platelet activation even further, a continuous feedback loop. Additionally, thrombin induces the formation of fibrin for the mesh stabilizing the clot. The self-reinforcing process of platelet activation, crucial in the formation of blood clots, is an obvious therapeutic target in conditions caused by inappropriately triggered blood coagulation.
The platelets then stick together to form a plug. They've quickly built a barrier that stops us from losing too much blood. However, this platelet plug isn't that strong, so it needs to be made stronger. A protein called fibrin does exactly that. In our blood, there are soluble fibrinogen proteins. At a wound, these soluble fibrinogen proteins are exposed to outside chemicals that aren't normally found in blood vessels. Like with the collagen and platelets, this exposure causes the fibrinogen proteins to turn into sticky fibrin fibers. The fibrin fibers form a mesh, holding all the platelets together and making a much stronger clot. More platelets, red blood cells, and other components in our blood all get stuck to the mesh, making it even stronger. This clot stops more blood escaping the body and also prevents nasty pathogens entering our body from the outside. The clot develops into a scab, which protects the wound as it heals, and new layers of skin form underneath. So really, all a scab is just platelets trapped in the fibrin mesh. It is like putting a plug in a sink. When the new skin is fully formed, the scab will fall off, revealing the lovely brand new skin underneath. A final thing to note, remember that I said the exposure to the collagen causes the platelets to stick together, and the exposure to the outside chemicals causes the fibrinogen to turn into sticky fibrin. Both the platelets and the fibrin only become sticky after the exposure. This means in a normal, healthy blood vessel, they won't randomly cause clots. So from this video, you should understand the magic of blood clotting. Platelets are first to the scene, closely followed by the fibrin fibers. Our blood clots so that we don't lose a lot of blood, and don't let lots of nasty pathogens into our body if we cut ourselves.
Our bodies have two main circulatory systems for transporting fluid, cells, nutrients, and waste: the cardiovascular, or blood system, and the lymphatic system. They are like two mass transit systems, with passengers, routes, and destinations. Both are made up of vessels, the train tracks and roadways, and passengers, the cells, molecules, and fluid. The blood system is like a high-speed train, the non-stop express. It carries cells, like red blood cells, platelets, and immune cells, and water, nutrients, and other molecules. The trains depart from the heart, the Grand Central Station, and branch off via smaller and smaller vessels destinations all over the body. At each destination, trains drop off their passengers at the capillaries, the smallest vessels in the body. At some destinations, passengers get off and deliver nutrients and supplies. At other locations, like the lungs, new passengers, like oxygen, hop on board. Each train returns to the heart to be pumped out to the body again. However, only 85% of the passengers riding the blood system get back on. The other 15% are picked up by the lymphatic system. The lymphatic system is like a high-tech taxi system which helps several important systems: the blood system, the immune system, and the digestive system. First, the lymphatic system returns extra fluid back to the blood system. When passengers are picked up at the lymphatic capillaries, they're called lymph. Lymph is made up of proteins, fats, immune cells, and extra fluid that has leaked out of the blood system, which needs to be returned. These capillaries merge with lymphatic vessels, which join into larger trunks, and ducts, which finally drain into the heart, returning the lymph to the blood system. Second, the lymphatic system helps the immune system fight infection. On its journey back to the heart, lymph is stopped by many strategically placed checkpoints for the immune system, which helps your body fight infection. These are called the lymphatic organs. They include your tonsils, adenoids, Peyer's patches, hundreds of lymph nodes, and the spleen, which acts like the largest lymph node in your body. The thymus and bone marrow have important jobs as well. At these checkpoints, immune cells look for threats. If a threat is detected, the lymphatic organ calls for help, and extra lymph floods in, carrying masses of immune cells. The increased amount of lymph causes the organ to swell up. After the threat is eliminated, the swelling goes back down. Finally, the lymphatic system helps the digestive system. At the small intestine, nutrients get on the blood system. However, some nutrients, like fat, are too large to get on board and are picked up by the lymphatic system. Since this lymph is rich in fat, it's called chyle. Chyle travels up the central lymphatics, the main central highway of the lymphatic system, up to the heart, enters the bloodstream, and finally travels to the liver, where its large, rich nutrients are digested.